We are really happy to be connected in a certain way with all of you, and we are happy to stream in more than 40 countries this morning here out of the HARTING Forum. It is important for us to get as close in touch with you as possible, so feel really free to use the chat box in the GoToWebinar meeting, to use all our LinkedIn channels, the HARTING channels, but also our personal channels to get in touch with us. All kind of questions will be consolidated and be answered also by the experts afterwards. We won't be able to answer all questions here on stage live because of our tight time schedule, but we will come back to this with you. And really getting in touch with you is so important and so funny also for us to have the exchange. Additionally, for us, it's also important to get feedback. So any kind of feedback will be recognized in the chat of the GoToWebinar meeting. So if we have to learn something on the technical side, or if you have wishes for further getting in touch with us, we are happy to do so. And now, it's really cool to have my colleague, Joachim Finke, here on stage, and he will talk about industrial Ethernet will change the industrial transformation. And as Joachim is one of also the brains, I call it, behind our week here, I'm really glad to welcome you on stage, Joachim, and looking forward for the first slot of the Industrial Ethernet Week 2022.
All right, thank you very much, Kilian, for the nice introduction. So my name is Joachim Finke. I'm Head of Product Management for the Network Interface Connectors at HARTING, and I'm very glad to have the honor to have the first presentation here in this Industrial Ethernet Week. So the topic for today is how Industrial Ethernet shapes the industrial transformation. And I have brought 3 topics with me. First one is we deal with the success story of Industrial Ethernet during the last couple of years. In a second step, we talk about the needs of the industrial, or let's better say digital transformation, and check if the existing technologies are really enough to cope with those requirements. And in a third step, we talk about new technologies where we are fully convinced that they will shape the future of the industrial communication. All right, so let's start with the first slide, the origin of Ethernet. So not industrial Ethernet, but the origin of Ethernet. Where does it come from? And if we see this picture here, it looks very nice. It's a nice beach. And what is it? It is a beach of Hawaii. So in fact, in 1970, the first wireless data network was founded by Dr. Abramson in Hawaii. And it was a network transmitting data packages by 2 frequency bands and a random mode for collision avoidance. Yeah, so very easy. And why did he invent this network? Very easy, because he would like to realize a cost-efficient way to communicate between the University of Honolulu and the islands surrounded. So this was really the basic start of Ethernet. And afterwards, even if the real Ethernet protocol standardized by the IEEE came in 1983, the Honolulu network was the first one. So afterwards, a really explosive performance growth has taken place. Yeah? So we had in 1983 the 10 Mbit standard. And here a little bit to represent the speed, I have inserted a bicycle on the screen. Afterwards, in 1995, a very, very big development step has taken place with fast Ethernet, so it's the 100 Mbit Ethernet. Why was this so important? Because for the first time, switching technologies, duplex data, communication mode, as well as the prioritization of packages was possible, and by this really an avoidance of data collision is guaranteed. And to be honest, this was a groundbreaking through step in order to realize the industrial Ethernet during the next couple of years and years. Afterwards, driven by all those enterprise data needs from ourselves in private life, as well as from data centers somewhere in the world, the speed extraordinary grows from 1 gigabit to 10 gigabit, and even to 25, 40, and even 400 gigabits. The yellow ones, they are not based on copper cabling. This is fiber optic. But those are speeds which I would say are not interesting for the industrial applications at this point of time. So this was the development of Ethernet in general, and the industrial Ethernet came around, I would say, the year 2000. Yeah, so as I mentioned, they take the fast Ethernet as a basis in order to work with real-time requirements. And I think it was Profinet published, or let's say origined in 2003. And further Ethernet-based fieldbus systems like EtherCAT and Ethernet IP and so on followed during the next couple of years. So what is the target of industrial Ethernet? The target was to really use the IEEE Ethernet for industrial networks, really to connect sensors, to connect drives and all the different things inside the machine, and to build a network, and to make use of the high data rates and bandwidths of the network, to make use of the nearly unlimited number of network participants inside the machine, and at the end of the day to have an overall TCP/IP-based communication from the enterprise level of the automation pyramid down to the control level and the field level. So this was the overall target. And as I mentioned, the fast Ethernet was a breakthrough because switching technology, full duplex data transmission, and the messaging prioritization is really a very, very important need for the use in the industry. What happened afterwards was the same that we saw for the fieldbus systems, that there is no one industrial Ethernet in the world, no. There are Ethernet-based protocols like Profinet, like EtherCAT, like CC-Link, like Ethernet IP, and all the different protocols you know very well. And now, approximately 25 years later, we all know that Ethernet has really penetrated the industrial market. Yeah, for example, the machinery and automation market, where we have different applications. For example, IP20, inside the cabinet, we have switches, we have converters. They are all based typically on Ethernet. If we go out of the cabinet, there are HMIs, there are sensors, there are I/O boxes, as well as actuators. And we all know that a lot of those devices really today are based on Ethernet communication, industrial Ethernet communication, no matter which protocol it is. It is the same with the robotic market. Even if the robotic market looks a little bit different, the applications within the robotic market is typically always the same. Yeah, so we have sensors and tools at the robot flange. We have address packs. This is the cable going down from the flange to the foot of the robot, where there is the Ethernet cabling inside. We have at each axis, there is a servo drive inside. We have a control unit, and all this is typically based on industrial Ethernet. To mention a last example, we have a look in the transportation business. So also here it started with wireless access points, with IP cameras and so on. So all the things which we as passengers use while we are traveling, but during the last couple of years, even the, I would say, safety relevant communication tools will switch and have already started to switch to Ethernet communication, industrial Ethernet communication. So means Ethernet has really become a very big place in industrial applications. If we have a look here, we see that in the last 25 years, 20 to 25 years, a fast development has taken place. We have now 65%, if we refer to factory automation, of yearly installed nodes, the market share, which are based on industrial Ethernet. And 1/3, so 28%, is still based on those traditional fieldbus systems. There is a small part of wireless communication technologies which will gain in the future up to at least a certain degree, because there are specific limitations for wireless technologies, but it doesn't matter. So this is the situation today, fieldbus 1/3 and industrial Ethernet a little bit more than 2/3. If we have a look on the applications itself inside the factory, so where is the industrial Ethernet and where are all those, I would say, traditional fieldbus systems? So one thing is clear, in the IT level, the standard Ethernet is dominating. If we go into the production hall, then all the different fieldbus protocols, industrial Ethernet-based fieldbus protocols are dominating. It's a green line. But now, to see where is the last third of traditional fieldbus systems today in the applications, it is indeed at the lowest level, it's a sensor and actuator level, like Profibus, CAN Open, and all the different things. And this makes the communication very complex. Because all those different protocols and technologies, they must be connected by gateways. They must be, you need specific people, yeah? If you would like to maintenance a network, if you would like to change a sensor, if you would like to add functions, it is always a very tricky and very difficult thing to realize those things. All right, if we now have a look on the industrial transformation, on the digital transformation in the industry, what does this mean? Because I personally have the feeling that we all say, oh, we are so digital, machines are full of automation systems, we have so many sensors inside, and is not everything existing which we need? So let's have a look on the digital transformation, the core. And I don't want to explain the IIoT or cyber physical systems. I would really try to break it down to a very simple level. And what is the digital transformation? It is the adoption of digital technologies in industrial applications. Yeah, from working life, we know this from the last couple of years already. Unfortunately, we need to work from home. It works, but it's one part of the digitalization. We have in companies, digital officers, so CDO, which were not existing the last 20 or 25 years, yeah, so also new development, and many, many things. But if we have a look on the performance of the company and the usage of digital technologies, then one thing is clear. Companies would like to use the new digital tools to become more productive, to create new offerings, for example, digital services or products which were not offered during the last couple of years. And they even would like to create new business models, yeah, platform models or whatever. Based on the digitalization. And this is very interesting to see because on the one hand side, digitalization offers a very big chance. On the other side, digitalization offers a very big risk, yeah, because if you take it right, you can develop. If you miss a trend, there always is a risk that you lose your business situation you have been established during the last couple of years. And this depends on many different factors. First of all, clear on the products the companies offer. So some products are more suitable for digital services and products, some are not. Then the size of the company is very, very important because not all machine builders especially are big companies like Trumpf or DMG Mori, which have probably hundreds of people being involved in R&D and especially with the digitalization of their products. There are companies, the typical machine builder in Europe, who has maybe 40 or 150 employees all in all, yeah? And they, of course, struggle, oh, is it a chance, it is a risk, do I miss any kind of trend? So this is a special thing with the digitalization of the industry. And beside everything, one thing is clear, one thing is really clear, and this I always heard from whatever machine builder I have visited during the last couple of years for my products. The access to the field data is the most important thing. It is key for the digital transformation in the companies. And we need to think back about the picture I have shown about this automation structure and where is the standard Ethernet, the industrial Ethernet, and where are all the field bus systems. And honestly spoken, we need to say that if we have a complete production hall with many, many different machines, so typically the machine builders, we think about our machine, but at the end of the day, there is an end customer like Volkswagen or whatever who has big parks globally and many, many machines. And all those machines, they work, they communicate. Everything is fine, within the machine at least. Or even with each other, but in a very more or less complicated way. But if we see it more precise, then we need to say that typically all the different machines talk different languages, yeah? So one talks, for example, English or American, the other one talks Chinese, the other one talks maybe Ukraine. So many different languages in such a production. This is one very important thing. Yeah, we know, we understand each other by a translator, by a gateway, but there are different languages. And the second one, the speed is fully different. Yeah, the speed and the performance of the network is fully different. There are machines, I put here some examples, so which are twittering or sending WhatsApp. Then there is another one on the right bottom side who is sending an email or a fax. And we all know brownfield, and we all know that the industrial machines which are working today will endure a lot of years until they will be scrapped and replaced by new ones. So means there are also machines using, I would say more or less very old communication technologies you can see here on on the left-hand side. So this is the situation today, and this makes it very, very, very difficult to deal with the things I just explained, digital business models and so on. So to explain this a little bit better, let's have a look into a machine. Yeah, no matter which manufacturer it is, I know that companies are working on this, on business models, new business models, where you do not sell a machine, where you do not lease a machine, where you provide a machine to a customer and say, okay, beside the monthly fee of a certain amount, you just pay per part. You don't need to do anything. I will control the machine, I will operate the machine, you just make the material flow, ensure this, and you just pay per part. Yeah, so there are companies working on this. But what does this mean for this tooling machine? So first of all, this tooling machine is not alone. Yeah, it gets somewhere in the material flow, the material it needs, and it's going to work on. Yeah, so it means a vendor-independent communication, horizontal, between the machines is needed. Otherwise, you cannot realize a fully autonomous operation of the machine, yeah, because this is a target. The companies, they don't want to sit in their office somewhere in South Germany and have a remote control and somebody logging in and checking if there is a problem. At the end of the day, the big target behind, and this is a marathon, it's not a sprint, will be to have a fully autonomous machine. Maybe starting with remote control, afterwards half remote control, and at the end of the day, by having gathered a lot of experience, having the fully autonomous machine. It's, by the way, it's very similar to what we see from autonomous driving, yeah? So there is not the traditional car where I drive myself and then there is the fully automated one. No, we all know there are different levels of autonomous driving. In the first step, the car could maybe keep distance. Afterwards, it is able now to drive a certain couple of seconds by itself, and maybe in many years, maybe, on certain roads, there might be really an autonomous driving car. And it's the same here for those machines. So it will be a step-by-step development. But as I mentioned, so the vendor-independent communication between the tooling machine and all the different machines around is very important. And it's not working if one machine talks EtherCAT and the other machine talks Profinet and so on. And then we have further communication standards there. You always have to make something special to make the communication work. Yeah, so this is the first point. Second point is you need, of course, a lot of more data you need for this, to gather data, like sensors and vision cameras, because while in the past, if there was a problem, somebody is looking inside the machine and saying, okay, this was wrong, it's now your responsibility as a manufacturer, because the customer just pay per part. So a lot of data must be collected, which is good for companies like SICK or IFM, even more sensors being used, but not to collect just the information, but really to give the information a standardized meaning. So it's called the semantic. Otherwise, it will not work if you would like to connect different machines and would like to make use of all the different sensor data if there is no semantic behind. And this semantic today is not existing at all between the different protocols. Semantic and also timestamp. Why timestamp? Because inside the machine, such a high performance process, you must, and if there is a problem, you must clearly directly see at a certain point of time how the different sensors and vision cameras, which did they detect. And sometimes this goes around milliseconds, yeah? And if you don't have the right timestamp for all the different sensors, the information afterwards you analyze could be without any value. Yeah, so this is very important, collect data in the right quality. And you need, yeah, so the vertical communication, as I mentioned, so you need a vendor-independent communication from the enterprise or the IT level down really to the machine. Because at the machine, the data is collected, and on the enterprise or software level, there are software tools which then make use of it and use, for example, artificial intelligence and try to identify some anomalies or whatever. Yeah, so these are the requirements a company who would like to make a pay-per-part business model fully autonomous, which they have to cope. And of course, you can say, oh, but why do we need to send this data all to the cloud? We have smart sensors. We can do everything here at the field level with the new technologies, and we don't need to send it to somewhere. That's also very easy. the customer is not selling, or the machine builder is selling hundreds of machines yearly, maybe even thousands, to China, to Europe, to USA, to Brazil, whatever. And of course, if there are certain error cases, the machine would not like to learn from the specific user. If somebody did a failure, or there was an error occurred in Australia and in China, all those data must be collected, that at the end of the day, all the other machine users benefit from this and don't do the same mistake once again. Yeah, so this is a very, I would say, easy to understand example how those new technologies, or what are the requirements for those machine builders. So if we now have a look on what is the requirement, and we know that with the existing technologies, we are simply not able to deal with this. Yeah, we need to change something. And we need to change something in a way that companies from many different fields, maybe competing today, are working together. Yeah, so, or in new wording, let's call it co-opetition. Yeah, competitors who work together in order to, at the end of the day, really reach something which is great for the overall industry. And this one here, this picture is not new. I think everybody knows about OPC-UA. So OPC-UA is the communication technology. It is not just a protocol, it's much more. It's the communication technology which is able to realize the vendor-independent communication between, on the horizontal, yeah, so between the machines, machine to machine. This is not new, and this is fully needed. And over 85% of all the today's existing industrial automation market companies fully support the sort of OPC-UA and say, okay, we participate to standardize this, and we will later on produce, develop products according to OPC-UA. But I would say this is not new. What new is, what I mentioned in the beginning, that the data of the field level has a very, very high importance for those digital applications. And here the OPC-UA field level communication initiative worked on an OPC-UA standard for the vertical integration, yeah, down to the machine. And this is called OPC-UA FX, so field exchange. And so together with the standard OPC-UA, we can reach, during the next couple of years, really a vendor-independent communication between all different levels, vertical and horizontal. As I mentioned, it is not just a protocol like Profinet, EtherCAT, or all the other. It's much more, because OPC-UA and OPC-UA FX, they really describe the meaning of the information all the different sensors are collecting. Yeah, so it's called the semantic, in order to make a plug and play, and afterwards to be able to deal with those information very, very easy. Yeah, and this, I can say you, is very complex. Yeah, so I know some guys who are working in those groups and who really do an extremely great job, and a job which is, yeah, working in very, very specific details. And I'm glad those guys are doing so. And we are coming more close that OPC-UA FX and all those things, they are working and coming to an end, because afterwards the big target is to make use of those information for data modeling by IT software tools. For example, like artificial intelligence or machine learning. Or there might be also other applications you can use, but this is the basic key. Yeah, so OPC-UA, OPC-UA FX is one extreme important step. The second step is, as I mentioned, so in the field level, of course, the real-time requirements are 100% needed. Yeah, they are mandatory. And the field bus, Ethernet-based field bus systems, we know from today, they are able to reach real-time requirements, but each of the protocols, they do it on their specific way. So it's nothing you can simply connect, plug and play, and it's working, no. And here we are very glad that with TSN, so OPC-UA over TSN, will enable OPC-UA FX to really deal with real-time requirements. And I'm glad that this is not just a proprietary technology, it really is it will become an IEEE standard TSN to make the standard Ethernet capable for real-time requirements. This is the second step, yeah, so language and speed. And we could now say, okay, that's it. Yeah, so we are, with those technologies, maybe it takes some time until they are really so that we can work with this, and there is not one TSA, there are different TSN standards, and it takes some time. We will discuss this later on this afternoon or late morning. But there is a third part. If we change from traditional field bus systems to Ethernet-based communication, then we need to connect a lot of field devices like sensors, like actuators, now with the Ethernet network. In the past, we did so when it was necessary. So I know a lot of sensors, for example, which are Ethernet-based. So this is the smallest part, I would say, of sensors, which are Ethernet-based, for example, vision camera sensors. And typically, I see even two connectors on it, one for data transmission and one for power supply. And typically, the width of the sensor is even the width is defined by the size of the connectors. Yeah? And if we now think about that, we connect a lot of more sensors to the Ethernet network, not, for example, because of the performance, but because we would like to have them at the network in order to have the information on the best and direct way. Then we need to cable further end devices with Ethernet cabling. And as we all know, today, the copper-based cabling is dominating in the industry, in the factory automation. And we have two ways. So Ethernet is a standardized technology. Also, the cabling is standardized by the ISO IEC and TIA, and you cannot use any kind of cabling. And the existing cable we can see on the screen is fast Ethernet. So we have two pairs of copper wires. One pair is transmitting information. The other one is receiving information. And we have the gigabit Ethernet cabling. There we have the double number of copper cables, or wires. So we have 4 pairs of copper wires, and they all transmit information and receive information. And you can imagine that if we would like to increase the number of sensors in the field, if we would like to connect them to the Ethernet network, the existing solution, they are not cost efficient and they are everything else than sustainable. And now the third technology comes into the game. It is called single pair Ethernet. You can see here on the screen. So as the name says, it is the Ethernet transmission by just one single twisted pair of copper wires. So means, all in all, it is a cost-efficient and very sustainable physical connection of end devices to the Ethernet network. So you can have a look on the back right-hand side. There is an Ethernet and single-pair Ethernet cabling, which is a little bit sized, from the view. You see just two pairs of copper, or one pair of copper wires, and on the left-hand side you have 4 pairs. So 2 copper wires compared to 8. And this technology is really mandatory to, at the end of the day, really connect the end devices to the Ethernet network. And to be honest, there are many new ways, for example, for hybrid technologies. Customers, so the one cable technology is a clear trend in the industry. We have, no matter if it's drive manufacturers or whatever, they all would like to have one cable technology instead of 2. And the problem is, if you use Ethernet and you have already 4 pairs or even 8 pairs reserved for data communication, then the hybrid cable connection and connector is already very big. But with this thing, with a 2-wire Ethernet, you have really new possibilities to make one cable technology in a very, very small form factor. And there are even different ways. So, like for power over Ethernet, there is power over data line for single pair Ethernet to use the same communication, and so data transmission and power supply by the same pair. But of course, you could realize hybrid connectors, for example, M8 hybrid connectors with 2 pairs for data transmission and maybe 2 pairs for power transmission, or even M12. So this offers complete new solutions for the industry. Very important is that single pair Ethernet, defined by the IEEE, is not just a connector. So here you see a typical device, or the electronic part of a device, and each device has certain things in common. It needs Ethernet connectivity. It needs magnetics to protect the Ethernet chip from impacts out of the network, to protect it. And as I mentioned, so we have the chips, the semiconductors for Ethernet. And each Ethernet device consists of those 3 parts. And you need to understand that if you would like to design an Ethernet device, all those parts will become new. So new connectivity, new magnetics, new semiconductors, because all are based on Ethernet communication. Great. So this is the basic outline of my presentation. just to sum it up, so with the existing technologies, we will not reach the targets which we have for digital transformation in the industry. So we need a vendor-independent communication and semantic, horizontal and vertical, which OPC UA will be able to offer. We need to reach the real-time requirements at the same time, so we need to use OPC UA over TSN to make it really capable for the applications at the end devices. And now the third technology to complete this is single pair Ethernet, the cost-efficient and sustainable physical layer, the two-wire Ethernet to connect the end devices really to the network. This is, I would say, the big picture of new technologies which will really shape the next couple of years and perfectly fit together. And luckily, we have built this Ethernet week in a similar way. So this was the first presentation. And by today, we will have, on the one hand side, a look to artificial intelligence. Kilian will introduce later on. We will have a discussion with other companies. So is this just a HARTING point of view because they would like to promote SPE, single pair Ethernet? Or how do other companies like SICK, like BNR, like KUKA think about this? We will have a great panel discussion today. And then, on tomorrow, we will have a close look on the device design of single pair Ethernet, of other solutions, and on the last day on cabling installation.